This is fundamental problem 3 from chapter 14. If the motor exerts a force of 600 plus 2s squared on the cable, determine the speed of the 100 kilogram crate when it rises to 15 meters. The crate is initially at rest on the ground. So we have a pulley in this problem. Before we begin to solve this problem, we're going to look at what happens in this situation when you have a pulley. So let's say that you wanted to lift the crate from 0 to 15, and you are going to do it at a very slow speed, so we can say the kinetic energy is going to be approximately equal to 0. So your initial gravitational potential energy, let's say that H is equal to 0 when the crate is on the ground. So we have mgh1 is equal to 0. And then when you're at 15 meters, you have mgh2, which is equal to the mass of the crate, which is 100, times little g, which is 9.81, times the height, which is 15 meters. And that gives you a gravitational potential energy of 14,715 joules. So now we're going to look at the equation that we have here, and when possible, I'm going to try and solve any problem in chapter 14 using just this equation, which is a combination of some of the other equations that we have for chapter 14. So we have the work U, which is equal to the integral of the force dotted with dr, and that's what we have here. And in this case, it's not the total work, it's the work done by non-conservative forces, or maybe we should say the forces other than the force of gravity and the spring force, because those are already being accounted for because we included the gravitational potential energy and the elastic potential energy. In this problem, however, we don't have any springs, so we don't have to worry about the elastic potential energy, so that simplifies the equation a little bit. And in our situation that we're looking at here, which is not what the problem is actually saying, but if we pretend that we're going to lift the crate very, very slowly so that the kinetic energy is equal to or approximately equal to 0, then we can get rid of the kinetic energy. And if you bring the gravitational potential energy initially is 0, so we could bring it over to the other side, but it's still 0. So we have the work is equal to the final gravitational potential energy. So we need to do a certain amount of work to bring the crate to a height of 15 meters. And then if the crate is moving faster, we have to do additional work for the kinetic energy that we have here. So now we're going to look at what happens when you have a pulley. So if we look just at what we have here, and I'm going to enlarge this, we have the cable up here, and the tension in the cable, if we assume it's a massless cable, is going to be the same at any point on the cable. So I have a force acting upward on this side of the pulley and on this side of the pulley, and those two forces are both equal to the tension in the cable, which they say the motor exerts a force of 600 plus 2s squared newtons on the cable, so that would be that force. So I'm going to call it F because it's called F in the problem. Okay, now I have another force acting downward on the pulley. I'm going to call that T because it's tension in this cable, which is a different cable. So I have two forces acting upward and one force acting downward. And if I look at the crate and I do a free body diagram for the crate, I have a force acting downward, which is the force of gravity, so that's m times g, and I have a force acting upward, which is the same as the force acting downward here, that's tension in this cable. Now, in our imaginary situation here, we were lifting the crate up at a very slow speed, and let's also pretend that that very, very slow speed is a constant speed also. So if the acceleration is equal to 0, then this downward force has to be equal to the upward force, so T is equal to 2 times F. And then from my free body diagram for the crate, I can see that the tension is equal to M times G. So I could say the force is equal to, that's half of the tension, so that's mg divided by 2. Well, this is the advantage of using the pulley. So the force that you have in this cable here is only half of the weight of the crate if, again, the acceleration is equal to 0. Does this mean that you need to do less work to lift the crate because the force in the rope is smaller than the weight of the crate? Going back to our equation here, we could use this smaller force, but remember this was equal to 0 and that was equal to 0 and that was equal to 0. So the work that you need to do to lift the crate to 15 meters is still 14,715 joules. So what happens here when you use the pulley? So the force is smaller, but the work still has to equal what we have here. So if the force is constant, we can say the work is equal to F dotted with delta R. So if the force is only half of what it would be without the pulley, then delta R is going to be twice as great. Well, this should make sense if you look at the picture, because if you are going to lift the crate up without the pulley, if you pull in 1 meter of rope, that lifts the block up 1 meter. But with the pulley there, if you pull in 1 meter of rope, that's only going to lift the crate up half a meter. Okay, so you have to do the same amount of work with or without the pulley. And if you have a pulley, the force in this rope here is smaller, but you have to pull more rope in to lift the crate by the same amount. Okay, so now we're actually ready to look at the situation that we have in fundamental problem 3. And what are we trying to find here? We want to find the velocity when s is equal to 15 meters. Okay, so I'm going to use this equation here. I can cross out the elastic potential energy, and unlike what they would do in the solution in the book, I'm not going to use, it would be equation 14-7, where this is the work done by all the forces. I'm going to use equation 14-20, which is what they use later on in the book, and use the gravitational potential energy because I like solving problems that way. And it also allows me to use the same equation no matter what section of chapter 14 we're in, unless it's the section with power and efficiency, in which case we'll be using these equations here. Okay, so the crate is starting from rest, so my initial kinetic energy is equal to 0, and then I'm going to choose the initial gravitational potential energy to be equal to 0, and it does not matter at what height you choose the gravitational potential energy to be equal to 0, because the only thing that's going to matter is the change in gravitational potential energy, unless they're specifically asking you what the gravitational potential energy is, in which case they'd have to tell you where to put the reference point. Because if you bring the mgh1 over to this side, that would be mgh2 minus mgh1, which is the change in gravitational potential energy. So, as long as you're consistent with where the height is equal to 0, you'll be good. So I'm going to say it's equal to 0 on the ground, and then here I have to figure out what force I'm supposed to use in this equation. So they give me the force that the motor exerts on this cable. Well, if I look at the crate here, why am I looking at the crate? Well, because it says the crate is rising 15 meters. So if you didn't want to look at the crate, if you wanted to look at, I don't know, a point on the rope instead, then that point is not going to be moving 15 meters. So we're looking at the crate, so we're going to look at the force on the crate. And by what we have over here, well, let's see, I said that this was true if the acceleration is equal to 0. If the acceleration is not equal to 0, then what we have here would actually be, see, if the pulley is accelerating upward, that would be, I'm running out of room, so let's look at this down here. 2 times F minus T is equal to the mass of the pulley times the acceleration of the pulley. Fortunately for us, we're going to assume at this point in the book that all the pulleys that we have are massless. So if the mass of the pulley is equal to 0, then we have 2F is equal to T, which is the same thing that we got when the acceleration was equal to 0. Okay, so I'm looking at the crate, and I have a force acting upward on the crate. That force is equal to T, but T is equal to twice F. So F is equal to 600 plus 2S squared. So for the work, I have the integral of twice 600 plus 2S squared dotted with dr. So this is the dot product. So now I have to think about what direction the crate is going in. So the crate is moving upward. Fortunately, this force F is also pointing upward. So I can just say dr because they're pointing in the same direction. And I'm going from a height of 0 to a height of 15. And this is equal to 1/2 times the mass of the crate, which is 100, times V2 squared, which is what I'm looking for. Let's just call it V, because it said find V. Okay, so we'll just call it V, plus 100 times 9.81 times height 2, which is 15. I already calculated that to be 14,715 joules, so let's just put that in. Okay, so now on the left-hand side, I have to integrate. So I have 2 times 600, that would be 12,000, integrated with respect to r, and that would just be r, plus 4 times s squared. Now, okay, why did I write it this way? It's an s here. Oh, because remember they said this thing earlier in the book that the magnitude of dr is equal to ds. That's somewhere here. The magnitude of dr is ds. So it was fine when I wrote it as dr here, but this is the magnitude, so I should call it ds. So that makes this s. And then this would be s cubed divided by 3. Then I'm integrating from 0 to 15. When I plug in the lower limit of integration, I get 0 for both terms. So this is equal to 1200 times 15 plus 4 times 15 cubed divided by 3, and that's equal to half of 100, which is 50, v squared plus 14,715. Okay, so we can look at what we have here and solve for v, and we get 12.5 meters per second. So you get to solve that on your own. The only thing I want to say before we finish this is if you are going to use this equation here, then you would be integrating the total force acting on the crate, which would be what we had here, minus the force of gravity, which is acting downward, which is why we have the negative sign there, because delta R is pointing upward, the crate's moving upward, so when you dot that with the force of gravity, you get a negative sign because the force of gravity is pointing downwards and dr is pointing upwards. And then when you integrate, you get the same thing we had there for this, and then when you integrate this, you get, well, m is constant, g is constant, so those can come outside, and then you have 15 minus 0, so that's minus m times g times 15. This is on the left-hand side of the equation. If you want to move it to the right-hand side of the equation, it would be positive, and that's the 14,715 that we had there. So if you're using equation 14.7 instead of 1420, which is what gave me this equation here, then that is what would be different.